Hi viewers, welcome to my class on mechanics of materials. In today's class, we will work out another numerical example to draw the shear force and bending moment diagram. Let us start. For the beam shown in figure, draw shear force and bending moment diagram. Locate the point of contraflexure if any. So the beam is supported at A and D. So it is an overhanging beam with a right side overhanging. So D is the portion where it extends beyond the support. There are two UDL acting with intensities 10 kN per meter and 20 kN per meter. And 2 point loads are acting on the beam, 30 kN and 40 kN. Now the support reactions are directly shown. They are vertical reactions at A and D. Let us calculate the reactions at the supports by taking moment summation with respect to A. So by taking the moment summation with respect to A, this UDL is for 2 meter, it's 20 kN acting at a distance of 1 meter. So 20 into 1 producing clockwise moment, and 30 will produce a clockwise moment, 30 into 2, plus 40 will produce a clockwise moment, 40 into 4, and this UDL part is 20 for 4 meter length. So 20 into 4, that is a load. It acts at a distance of 4 plus center of 4 meter, that is at D only. The resultant UDL will act at D, and that will produce a clockwise moment. So 80 into 6, 80 is the resultant load, 20 into 4, it will act at D, and the distance is 6. So 80 into 6 clockwise moment minus RD into 6, that is equal to 0. That is a moment summation. So you get 10 into 2, 10 is the intensity of the load, into 2, that gives a load, into the distance is 1, plus 30 into 2 clockwise moment, plus 40 into 4 clockwise moment, plus 20 into 4 is a load that will act here, the center of that span. 20 into 4, the distance then is 6, 20 into 4 into 6, and this will produce an anti-clockwise moment minus RD into 6 is equal to 0. So from that you get RD as 120 kN. Now to find out RA, you can find out the resultant downward load and subtract RD from that. So the resultant downward load is 20, 10 into 2, 20, plus 30, plus 40, plus 80, minus 120. 10 into 2, this UDL, plus 30, plus 40, plus 20 into 4, 80, minus 120. And don't get confused taking this as a positive. I am just only summing up the magnitudes. Okay. So total downward load I am calculating, the magnitude of total downward load I am calculating, and then subtracting the reaction at D to get the reaction at A. Or you can sum up as RA minus 20 minus 30 minus 40 minus 80 plus RD is equal to 0, and then find out RA. Now let us find out the shear force at various sections. Since UDL is acting, you will take two sections in the portion AB, immediately right of A and immediately left of B. Right of A, you have 50 kN. When you take a section here, immediately right of A, only one force is there. So plus 50 is the shear force there. Now left of B, plus 50 minus this part of UDL, its complete UDL is coming when you take a section immediately left of B. So plus 50 minus this load is 20. So 50 minus 20, 10 into 2, for 10 kN per meter for 2 meter. So it is 20. 50 minus 20, you get 30. So that is immediately left of B. When you move to the next section, BC, You have to take only some anywhere in between B and C. So when you take a section here, the load change is only 30 kilonewton. We are moving from left of B to the section BC. So here you have 30 minus 30, which will give 0 here. So shear force anywhere between B and C is 0. So let us sum up from left side. Total force, this is already there, 30. So let us sum up again, 50 minus 20 minus 30, that will give the shear force here. So 50 minus 20 minus 30, 0 kilonewton. So this part is not subjected to any shear force. Now let us take a section here immediately right of C. Immediately right of C, if you take, this is a shear force here in the portion BC, from where you are just moving immediately right of C. So that will add this force minus 40. So 0 minus 40, you get shear force as minus 40 immediately right of C. Immediately right of C, will get the shear force as minus 40. So this part, 50 minus 20 minus 30, that is 50 minus 20 minus 30, and when you are in here, another minus 40. So that will give minus 40 as the shear force. Now immediately left of D. So here you have minus 40. When you move to the left of D, this part of UDL, that is 20 kilonewton per meter intensity for 2 meter. So that part of UDL will be 40 kilonewton. So here you have minus 40. When you move to this minus 40 minus 40, you will get minus 80. Summing up again, this part I have already shown, that is minus 40 minus 20 into 2, that is this part of load, and since it is downward, minus negative shear force, so minus 80 you get. Summing up, 50 minus 20 minus 30 minus 40, and this part of UDL, 20 into 2 minus 40, that is the shear force left of D. Now immediately right of D, when you move, left of D you have minus 80. Immediately right of D, it will be minus 80 plus 120. So this is a force added. So minus 80 plus 120, you will get plus 40 here. Plus 40. You can sum up from left side again. 50 minus 20 minus 30 minus 40. This part of UDL is 20 into 2. That is minus 40 plus 120, that is the shear force immediately right of D. Now when you move to left of E, right of D you have 40, right of D is 40, the shear force is 40. 40 minus this part of UDL, only this part of UDL you can add, that is you are moving from here to here, left of E. So 40 minus 40, you will get 0 here. Left of E you get 0, even at E it's going to be 0 because no point load here. So I am summing up from left side. So this is a section taken left of E, plus 50 minus 20 minus 30 minus 40. So I have treated this as two separate UDL. Up to here one UDL, then another UDL. That is not required. You can take this two, you can club. So total 20 into 4 meter, 20 into 4, instead of writing minus 20 into 2 2 times, that is this portion and this portion separately treating, you can take 20 into 4, which is minus 80. So minus 80 plus 120, that will give 0, and at E also it will be 0. So we need only that right of D and left of E, that will give the nature of variation. Here immediately right of C and left of D, that will give the variation here, and right of A and left of B, which will give the variation here. So once you get the variation at the ends, you can plot the variation of shear force. Here no variation, so only one section, and you got the shear force as 0. Now let us calculate the bending moment. Bending moment at A is 0, bending moment at B is 50 into 2. 50 is producing clockwise moment. So 50 into 2. This load is 10 into 2 meter. This acts for 2 meter. So 10 into 2, it acts at a distance of 1 meter and produces negative moment. Downward force will produce negative moment with respect to P. So upward force, positive moment with respect to P. 50 into 2 minus 10 into 2 into 1. So that will give 80 kilonewton meter. Now if you calculate the bending moment at C, 50 is producing a clockwise moment, 50 into 4. This part of UDL is 10 into 2, 20. 20 acting at a distance of 1 meter, at the center of 2 meter. From C it is 2 plus 1. This is 2 plus another 1. So 20 into 3. So that will produce a counterclockwise moment. So minus 20 into 3. Again 30 is 30 produces counterclockwise moment. Minus 30 into 2. So 50 into 4 minus 10 into 2, that is 20 into 3 minus 30 into 2. So that is the bending moment at C, and you got the same value, 80 kilonewton meter here. So bending moment at B is 80 kilonewton meter, C is also 80 kilonewton meter. That is because shear force is 0 for this entire section. Whenever shear force is 0, bending moment has to be either constant or you should have a peak. So here for the entire length shear force is 0. So bending moment you have constant value for the entire length of the beam. At D, if you calculate the bending moment, you have 50 into 6. The bending moment due to 50 is 50 into 6, and this UDL is 20 kilonewton. 20 kilonewton acting at a distance of 1 plus 4, 5 meter away. So minus 20 into 5. 30 is acting at a distance of 4 meter. So minus 30 into 4. 40 is acting at a distance of 2 meter. So minus 40 into 2. And this part of UDL is also producing a moment with respect to D. So this part of UDL is 20 into 2, that is 40 kilonewton, acting at a distance of 1 meter. Since we are only taking this portion of UDL, 20 into 2 acting at a distance of 1 meter. So that will produce a negative moment. So minus 20 into 2 into 1. So 50 into 6, and this 10 into 2 into 5, minus 30 into 4, minus 40 into 2, and this part of load is 20 into 2 acting at a distance of 1 meter. So minus 20 into 2 into 1. That will give bending moment at D as minus 40. Now bending moment at E is going to be 0. When you calculate the bending moment at E, you are considering all the loads. That will has to give the bending moment at E as 0. Now to draw the shear force diagram, we know the shear force right of A as 50, left of B as 30. So 50 to 30 has to decrease in that section AB. And for the portion BC we got 0, so there is no shear force acting for that section. And for the section CD, the right of C we know minus 40, left of D we know minus 80. So minus 40 to minus 80, it has to vary in that section CD. So minus 40 to minus 80. Now for this section, right of D we know plus 40, left of is 0. So 40 to 0 is the variation for that section. So here it will change from minus 80 to 40 because of this point load. Left of D minus 80, right of D plus 40. So that change is at D minus 80 to 40. Overall change is 120 because of the point load. When the portion BC it was 0, it has suddenly changed to 40, minus 40 because of this downward point load, minus 40. Downward load will decrease the shear force. It has decreased from 0 to minus 40. Here, because of the point load, it has decreased from 30 to 0, it has decreased. Here again you can see it has increased from 0 to 50 and then decreasing because of UDL. So point load will increase the shear force at that point and UDL will decrease continuously over the length of the beam. So if it's a downward UDL, it will decrease the shear force. And if you are getting an upward UDL, rarely you get upward UDL, then it will increase the shear force. Now to draw the bending moment diagram, you have the bending moment at A0, at B we have calculated as 80 kilonewton meter. So 0 to 80 and the variation is going to be parabolic. Now while plotting the parabolic variation, there is no peak for the bending moment. So bending moment you should plot without a peak, since there is no change of sign for the shear force. Suppose you get a change of sign for the shear force in this portion, then you should draw the bending moment with a peak. So peak coming in the point where shear force is 0. So here there is no change of sign for shear force. So you should draw the bending moment curve parabolically but constantly increasing. There is no peak for this. And we should not increase beyond this point. If you draw a horizontal line, all the part of this curve will be below that line. Then for this section, the bending moment is constant. At C also we got bending moment as 80. B is 80, C is 80. And we can also recall that relation which you have studied is dm by dx is equal to V. Rate of change of bending moment is equal to shear force. So here V is 0. So dm by dx should be 0. dm by dx means rate of change of bending moment with respect to distance is 0. So rate of change of bending moment is 0 means either bending moment has to be a constant or slope of the bending moment curve should be 0. So here bending moment is constant because entire length it is shear force is 0. So bending moment has to be constant. If at any point shear force is coming to 0, rate of change of bending moment will be 0. Now at D we got the bending moment as minus 40 and also we know that variation of bending moment is parabolic. From 80 to minus 40 it has to vary parabolically, once again without a peak. There is no peak because shear force is not changing its sign. It's negative from left hand to right hand. There is no change of sign. Always the shear force is negative only. So without a peak, no peak here, so continuously going down and it's reaching minus 40. Continuously the bending moment is decreasing to minus 40. At E we know bending moment is 0, so you can change it like minus 40 to 0 and again parabolic variation. While drawing this parabolic variation, always you see that concave side is down. So parabolic variation for bending moment will be always drawn with the concave side down. So that will be the nature of variation. So it will not vary like this. You should not draw it like this. Again, you should not draw it like this. For bending moment curve I am talking. So okay, bending moment curve you should always draw with the concave side down. And this is how the parabolic variation for bending moment changes. So we got the shear force and bending moment diagram. Now you can observe that there is a point of contraflexure and this point you should locate, and to locate that point you can write down the bending moment equation for this section, this particular section. This section means CD. So you have to take a section plane here and write down the bending moment equation for that section and equal to 0. Now let us write down the bending moment equation for that section. We will take a section here and at a distance x, because the point of contraflexure is coming in the section CD, we will take a section there, the distance is x, so we will write down the bending moment equation for that section. 50 is producing a clockwise moment, so 50x. Now this part of UDL is 20 kilonewton, but 20 kilonewton, since x is a variable, you cannot get directly the value of distance. You should take in terms of x. So the 20 kilonewton, we know it is acting at a distance of 1 meter from left hand. So from this section it is going to be x minus 1 meter, this distance 1 meter. So it is acting here. So from here the distance is going to be total x minus 1. So you have to subtract these distances. From x you should subtract the location of the load from left hand, that will give the distance of that load from the section. So 20 into x minus 1, so that will give the distance. So 20 is the load, x minus 1 is the distance, so that will produce a negative moment. Next load is 30, the distance once again total is x, you should subtract the location of that load, so that is 2 meter. So 30 into x minus 2. Next 40 is producing an anti-clockwise moment, and to get this distance total x subtract 4 meter, that is location of that load is 4 meter away from left hand, subtract that 4 meter from x, which will give this distance. So minus 40 into x minus 4. Now next part of the load is this UDL. This UDL is 20 is the intensity of load, and this distance you should know. This distance is x minus 4. X minus 4 is the distance. Okay, 4 you should subtract, so which will give the distance x minus 4. So 20 is the intensity of load into the distance is x minus 4. So 20 into x minus 4 gives the load, and the resultant load will act at the center of this distance. So x minus 4 divided by 2, okay, that will be the distance. X minus 4 divided by 2. This is the centroid of the load, the distance of centroid of load from the section, x minus 4 by 2. X minus 4 is the length, this length, x minus 4, 20 intensity into the length is x minus 4, and the centroid of that load is x minus 4 by 2. So that will give the bending moment equation. You can reduce this, 50x minus 20x plus 20 minus 30x plus 60 minus 40x plus 160 minus 10, this 2 you cancel, minus 10 into x minus 4 square, x minus 4 into x square minus 8x plus 16. Now if you reduce this, you get x square minus 4x minus 8 is equal to 0. After dividing by 10, you will get x square minus 4x minus 8 is equal to 0. So you can reduce this into a quadratic equation. So it's going to be a quadratic equation. So we'll get after dividing by 10, we'll get x square minus 4x minus 8 is equal to 0. Now you can find out x as minus 4 minus b plus or minus root of b square minus 4 square minus 4 into a is 1 into minus 8 divided by 2a. By solving this you will get x as 5.464 meter and minus 1.464 meter. Two values of x you will get to satisfy this equation, but whichever value is within our required portion you should take. So minus value is not at all relevant here. So x is 5.464, which is coming in this section. So this should be taken as a solution. So the distance of that point of counterflexor from left hand is 5.464 meter. So that means this distance is 5.464 meter. So we got the shear force diagram, bending moment diagram. We have marked all the significant values of bending moment and shear force, and we also located the point of counterflexor. With that we complete the diagram. And that's all for today. Thank you for watching.